Welcome to this session. In previous session, we have learned that when a molten iron melts, when a molten iron solidifies, what is happening? We got different forms of iron at different temperatures, right? So what was happening there? That the mechanical property of the that solidified forms such as density, elastic constant, strength, ductility, these properties changes with respect to time, with respect to temperature, as the crystal structure changes. So what we were doing there, then we propose that how the problem was that how we can enhance the mechanical property of iron which is at different forms. So one solution came that we have to add various proportion of carbon in pure iron. So we ended with this conclusion in previous lecture. So in this lecture we will try to explore the iron carbon phase diagram system. So before going to this lecture, just I want to recapitulate some important points which is very important for understanding this section. So let's try to explore. First is Gibbs phase rule. Gibbs phase rule. So we have learned this is the general form of Gibbs phase rule. This is P plus F equals to C plus N. In thermodynamics, if you remember, we have taken P plus F equals to C plus 2, right? So let's try to explore. Let's try to explore what is this P, what is this F, C, and N. Here P is number of phases, F is degree of freedom, C is number of components, N is number of variables, used, number of variable used in the study of internal phase of alloy. So here actually what happened, N depend on temperature, it depend on pressure, it depend on composition, but what is happening in our phase diagram study, we keep pressure constant as 1 atmospheric pressure, and composition is also we take a constant, we kept constant. So only variable left is the temperature, right? So this is constant, composition is also constant, right, at a particular composition. So only this property will vary. So the general form of Gibbs phase rule will be P plus F equals to C plus 1. This is the Gibbs phase rule for phase diagram. This is the Gibbs phase rule for phase diagram. So now here let's try to define f. F is our degree of freedom. Now degree of freedom is defined as the number of variables number sorry number of variables which can be altered independently without affecting the number of phases existing in equilibrium. Now suppose if degree of freedom is 0, then the resulting transformation in alloy is known as invariant reaction. If degree of freedom is 1, then the resulting transformation in alloy is known as univariant reaction. Now if degree of freedom is 2, the resulting transformation in alloy is bivariant reaction. So till now we have learned only PBSN diagram. So there we got one eutectic point, and we will explore it just in 2 minutes. That at eutectic point we get degree of freedom as 0, right? So that eutectic point is called invariant reaction point or invariant point, right? So let's try to explore it more. So as we have seen in case of PBSN diagram, we get the phase diagram that was something like this. Okay, so what was the notation? Alpha was here, beta was here, and this phase was liquid, this phase was alpha plus L, this is what beta plus L, and this is what invariant point. If we cool liquid, if we cool at this fixed composition at 62 weight percent, for 62% of this PBSN, this is so 52 weight% of SN. So if we cool from liquid at this composition, we will get what? We will get alpha plus beta. So this point 1 was termed as eutectic point. Eutectic means easy melting. Eutectic means easy melting. Now let's try to apply Gibbs phase rule for this eutectic point. So this will be, so let's start what is happening at eutectic point here. L will transform. This will be reversible reaction. It will transform into alpha plus beta. This is what liquid phase. This is what solid 1, and this is what solid 2, right? And this is what liquid phase. Here if we cool, we will get alpha plus beta phase, and if alpha plus beta phase is getting heated, so we will get liquid phase. So you can see here we have phases. We have 3 phases: solid 1, solid 2, and liquid, right? And component is how many we have. This PB and SN component is 2. Degree of freedom is unknown. So now let's try to apply Gibbs phase rule here. We get, so here it will be only 1, because as we have discussed earlier, because pressure and compositions are kept constant here, so F will be C plus 1 minus P. C is 2 plus 1 and P is 3. So this is F is 0. F is 0. F is 0. F comes out is 0. Where? Here. At eutectic point, degree of freedom we obtain as 0. Now let's try to see what is going to happen in case of iron carbon phase diagram. So let's try to draw it. So इसको काफ़ी धैर्य के साथ ड्रॉ करिएगा. इट इज़ वेरी इम्पोर्टेंट एंड वेरी ट्रिकी. जैसा जैसा मैं बता रहा हूँ आपको वैसे वैसे स्टेप फॉलो करने हैं. इट इज़ वेरी ट्रिकी. So what we have learned in PBSN, we have only one invariant point. ठीक है. So here we will have 3 invariant points. So what we have to do, just draw first 3 points: point 1, point 2, and point 3. 4.3 somewhere here. Okay, then what we will do, just draw one horizontal line. Draw one horizontal line from here. ठीक है. Then one horizontal line from here to here. पूरा यहाँ तक ड्रॉ करना है. Then again one horizontal line from here to here. Okay, now what we have to do, इसको यहाँ पे पकड़ना है, इसको पकड़ना है, and we have to focus on these points. Now what we have to do, इसको यहाँ से join करिए and join it till here. We will get this point. फिर इस पॉइंट को यहाँ से ज्वाइन करना है, इस पॉइंट को यहाँ से ज्वाइन करना है, इस पॉइंट को यहाँ से. ओके, एंड सिमिलरली इस पॉइंट को इस पॉइंट को यहाँ. सो आई होप यहाँ तक क्लियर होगा. सो फर्स्ट हमने 3 पॉइंट बनाए, फिर 3 पॉइंट को वी हैव एक्सपेंडेड फ्रॉम लेफ़्ट एंड राइट, लेफ़्ट एंड राइट, लेफ़्ट एंड राइट. फिर हम लोगों ने ये सेक्शन बनाया. जस्ट ड्रॉ 2 लाइंस फ्रॉम दिस पॉइंट हियर, हियर एंड हियर टू हियर. राइट नाउ then we will connect this line. Okay, and from here we will connect this line. Okay, and from here we will connect to this line. और ये 2 पॉइंट I will add these 2 points here. Okay, so now let's try to write the different temperature what at the various point. So this point is corresponding to 1539 degrees Celsius, and this point is correspond to 1400 degrees Celsius. This point is corresponding to 910 degrees Celsius. And yes, one important point is that this point is 4.3. Okay, so on y-axis we have temperature in delta in degrees Celsius, and on x-axis we have carbon. Here the maximum amount weight percent of carbon is 6.67 weight percent of carbon. And what is happening here, so if we add carbon above this weight percent, then there will be no intermetallic compound will form. So the maximum salt solubility of carbon in iron is 6.67 weight percent. So we take it as 100% Fe3C, 100% Fe3C. This is the intermetallic compound of iron and carbon, right? So let's try to explore it more. So it's here we will get 4.3 weight percentage of carbon, and this location we will get 2.1 weight percentage of carbon. This location is 0.8. This location is 0.02. This location is 0.1. This location is 0.2. This location is 0.5. okay, so this is 0.002 and this is 0.1. So this is clear. I think this section will be a little bit narrower. Okay, fine. So this reason is called delta iron. This reason will be delta iron. Okay, and this is what liquid domain. This is liquid domain, and this reason is alpha. This reason is alpha. This is called ferrite. This is alpha and it is called ferrite, and this reason is gamma. This is called austenite. This is austenite, and the temperature corresponding to this point it will be 1150 degrees Celsius, and this will be what? Eutectic point. This will be eutectic point. Okay, this point will be eutectoid point. Okay, so these are the different points. Okay, and this point is called peritectic. This point is called peritectic point. So now let's try to write what are the phases present here. So this is liquid phase. Okay, this is liquid phase, this is delta phase. So guys, can you tell me what phase will be this? I hope it is clear from 1 to 1 rule that it will be delta plus liquid phase. Okay, and this is alpha, this is gamma, this is alpha, this is gamma. So what phase we will get? In this reason it will be alpha plus gamma. Okay, and this is gamma, this is liquid. This phase will be what? Gamma plus liquid phase, right? And now let's see what is happening on right side. So as we have discussed earlier, so this vertical line will represent cementite. Fe3C cementite. This is what? Single phase. This is single phase reason. Okay, so this is what? Fe3C. If Fe3C is present on this line, so can you tell me what is going to happen in this phase, in this reason? This will be what? L plus Fe3C, okay, L plus Fe3C. Okay, now, and this reason will be what? This reason will be what? Delta plus gamma. This reason will be delta plus gamma. Okay, and any other reason? So I hope we have mentioned all the reasons. Now let's try to write. So this is eutectoid point. This is eutectoid point. So and this is eutectic point. Okay. So the reason ahead of this eutectic point will be eutectic eutectic region. Okay, and the region below this will be hypoeutectic region. Hypoeutectic this region will be what? hypoeutectic region, and this is eutectic point. So इसके आगे क्या होगा यार? This will be hypereutectoid region, और इसके पहले क्या होगा यार? This will be hypoeutectoid. This will be hypoeutectoid region. Now, one interesting property which we can observe from this figure. Now, if we focus on this 2.1 weight percentage of carbon, 2.1 weight percentage of carbon. So the reason which is less than 2.1 weight percentage of carbon, this is termed as steel. This is steel, and the reason which is beyond 2.1 weight percentage of carbon, this is called cast iron. This is called cast iron. So this is the steel. So you can see this steel, we got steel in this eutectoid point region. So in our whole study, this point will be very important. This point will be very important to understanding the microstructure of the steel. So steel, as we already know, that in our human civilization, steel has played very important role in our daily life, right? Where you are sitting in a room, you can see you will get a lot of items made up of steel, maybe your uh, utensils, glass, chammach, thali, plate, and many other uh, material made up of steel which we use in our daily life. So this is what steel, right? So now let me recapitulate some important point. Alloy, less than 2.1 weight percent of carbon is called as steel. Alloy greater than 2.1 weight percentage of carbon is known as cast iron. So you can see that if alloy concentration in alloy the carbon concentration is greater than 2.1 weight percentage, so in this region we will get eutectic point. In this region we will get eutectic point, and we have already discussed what is the meaning of eutectic point. It means that easy melting. So what is going to happen here, if uh, if the composition of alloy is greater than 2.1, the melting will be very easy if it is going from solid to liquid, or if it is going from liquid to solidification. Solidification will be happen very quickly at this 4.3 weight percentage of carbon, this composition of carbon. And if we are heating from this region to this region, so melting will be very easy. That's why in casting this kind of iron is used. That's why we named it as cast iron. So 4.3 weight percent alloy melt at very low temperature, and hence this low melting temperature is beneficial for casting process, right? That's why we get the name cast iron. Okay, so this is all about the iron carbon phase diagram. Now let's try to see what are the different phases present in iron carbon diagram. Phases in iron carbon diagram. So first phase, which we denoted by L, this is what liquid. Another phase which we denoted by delta ferrite, it was denoted by delta. This is interstitial solid solution of carbon in delta iron, which is BCC in nature. It exists at high temperature. Then next phase which we represented is gamma austenite. So this was denoted by gamma. This is interstitial solid solution of carbon in gamma iron, which is FCC in nature, Okay, and next is alpha ferrite. It is denoted by alpha. This is interstitial solid solid solution of carbon in alpha iron, which is BCC in nature. This form at low temperature, and last one was Fe3C. This is what cementite. This is intermetallic compound of iron and carbon. This is intermetallic compound of iron and carbon. This is having orthorhombic crystal system. Right, so these are the different phases present in the iron carbon diagram. Now let's try to see what are the reactions taking place at invariant point. So we will get reactions at invariant point. Invariant point reaction. So if we will take peritectic point, so what will be going to happen here? So this delta plus liquid will be cooled into gamma at 1493 degrees Celsius, right? And what is happening at, let's try to see what is happening at eutectic point. So here liquid will transform into gamma plus Fe3C, and this is what gamma plus Fe3C is known as lead burite. This is known as lead burite. It is defined as eutectic mixture of austenite gamma and cementite Fe3C. Lead burite is defined as eutectic mixture of austenite gamma and cementite Fe3C. Okay, then at eutectoid point we will get gamma will be converting into alpha plus Fe3C. This will be at 725 degrees Celsius. This happened as 1150 degrees Celsius. Okay, now here in whole iron carbon diagram, eutectoid reaction is very important. Now the funda is control of eutectoid reaction is what gives us control of microstructure of steel through various heat treatment. So we will explore this eutectoid point, that how we are getting different microstructures in steel.